quick break from the rules to go back to differentiability so you can complete that differentiability assignment. We're looking at differentiability when we've got a piecewise defined function here. So take a look at this function. F of x is equal to the quadratic 2x squared plus x minus 5 if x is less than or equal to 2. F of x is equal to x cubed minus 3x plus 3 if x is greater than 2. So the piecewise defined function says you're going to use one or the other depending on what your input is. If the input is less than or equal to 2, use the top function. If the input is greater than 2, use the bottom function. So two tasks here. The first one is this function continuous at x equals 2? So we think back to continuity from a long time ago. A function is continuous if the limit of the function as x approaches that value is equal to the value of the function. All right, so we got to figure out what f of 2 is going to be for starters. All right, well, if f of 2, that means we're going to look for when x is 2. If x is 2, that falls under this condition, which means we're going to plug 2 into the top function. So we're going to have 2 times 2 squared plus 2 minus 5. Okay, all I've done is I've replaced x with 2 in my top function because that's the one we have to use based off of the condition. So if we simplify this quickly, 2 squared is 4, and then we double it so we get 8, plus 2 minus 5. 8 plus 2 is 10, minus 5 is 5. Okay, so I know that f of 2 is 5. Now, in order for the function to be continuous, the limit as x approaches 2 all of the function must also be 5. Let's see if that's true. Now, the limit will exist if the limit from the left is equal to the limit from the right. We already know what the limit from the left is going to be because we would plug, these are numbers that are less than 2, so like 1.999, but it's so close to 2 that we can use 2, and if we plug 2 into here, we know that we get 5. Okay, so just over here on the side, I know that the limit as x approaches 2 from the left of the function, that's equal to 5. Okay, the question is, what about the limit as x approaches 2 from the right of the function? Will that also equal 5? Well, let's find out. Let's plug 2 into the bottom part. If we plug 2 into the bottom part, again, I'm just doing it over here on the side, we have 2 cubed minus 3 times 2 plus 3. All right, 2 cubed, 2 times 2 times 2, that would be 8. 3 times 2 is 6, so we have 8 minus 6 plus 3. 8 minus 6 is 2, plus 3 is 5. So the limit from the right will also equal 5. So since the limit from the left is the same as the limit from the right, that means that the limit exists and it's equal to that number. So since the function's value is 5, and the limit's value as x approaches 2 is 5, then we can say yes, the function is continuous at x equals 2. Now that's a review. Okay, we did that a long time ago. But now we have a new question. Is the function differentiable at x equals 2? In order for the function to be differentiable, a piecewise defined function to be differentiable, at the point where we change from one part to the other part, we need to see if the function's derivative is nice and continuous as well. So we got to get our derivative, and then we have to plug in 2. If we get the same value for both the top and the bottom, we would answer yes. If we don't get the same value, then we would have to answer no. But for starters, we need to actually get the derivative. So let's do that. We need f prime of x. F prime of x, okay, we just derive the top and we derive the bottom. The derivative of 2x squared plus x minus 5. Let's use our rules. 2x squared, all right, the 2 up here will come down and multiplied by the coefficient of 2, so we have 2 times 2, or 4x. And then the derivative of x, well, the coefficient is a 1 right there. It's not written, but it's there. So that coefficient is going to come down. So we have 4x plus 1. All right, the derivative of x will always just be 1. Okay, and then we have the constant of 5. 5 derives to 0. So our top derivative is 4x plus 1, and that's valid if x is less than or equal to 2. Our bottom derivative, all right, well, here we go. X cubed, we've done that a bunch of times. Its derivative is 3x squared. Minus 3x. So we're deriving 3x. The 3 is the coefficient, so that's going to move down. So we have minus 3, and then we have plus 3. That's a constant, so it derives to 0. So 3x squared minus 3 is the derivative of the bottom part of our piecewise defined function. And this derivative is valid when x is greater than 2, because the conditions don't change. So the question is, what happens at x equals 2? Well, we're going to plug 2 into the derivative, okay? If we get the same value in both the top and the bottom, because that's our switching point when x is 2, then we'll say yes, our function is differentiable at x equals 2. If we don't get the same value, then we'll say no, it's not differentiable at x equals 2. So let's plug in 2. If we plug 2 into the top function, would you all agree that we get 9, right? 4 times 2 plus 1. Make a little note here, we're going to get 9. If we plug in 2 in the bottom function, we have 2 squared, which is 4. We triple it, that's 12. Then we subtract 3. 12 minus 3 is also 9. So we get 9 as well. 9 is equal to 9, so our answer is yes. Our function is differentiable at x equals 2. Why? Because when we plugged 2 into both parts of the derivative, because that's where the derivative changes, we got the same answer. That means the derivative just picks up right where it left off, okay? Which means that our function is differentiable at that spot.